Welcome to Electrical Technology 1. This is Module 3 on electrostatics. In this chapter, we will learn about the basic principles of electrostatics. The capacitors are explained in terms of capacitance and capacitor dimensions. Capacitors are also outlined in terms of capacitor types and capacitor characteristics. Capacitor charge and discharge action is described in and actual measurements are taken in circuits. Voltage and charge on capacitors in series and in parallel electric circuits are calculated. Energy stored in a charged capacitor is calculated. Safety principles on capacitors are explained. Capacitors are outlined and relevant to different industrial applications. A capacitor is an energy storing device which is made up of two or more conducting plates and an insulating material which is also called the dielectric between the two plates. As you can see the schematic symbol of a capacitor in figure 1, it shows the two conducting plates and the dielectric, which is the blue part between the two plates. Figure 2 shows the symbol of a capacitor that we use on circuits. We have three types: the fixed capacitor, which does not show the polarity, so you can connect it anywhere in a circuit. Then we also have the polarized capacitor, which has the polarity positive and negative. And then we also have a variable capacitor. That means you can vary the value of the capacitor in farads. Capacitors are used for storing electric charge in applications that require a quick discharge, for example, a camera flash, and also play a major role in turning circuits of TVs and radios. You should be cautious when connecting a polarized capacitor in a circuit because they are explosive if they are connected wrongly. So the positive part should be connected to the positive supply voltage. The ability of a capacitor to store charge is called capacitance, and the unit in which capacitance is measured is called farad. The capacitance of a capacitor is affected by few parameters, which are the area of the plate, the distance between the two plates, which is the dielectric distance, and the material used for the dielectric. The formula in equation 1 is used to calculate the capacitance of a capacitor, whereby the area is calculated using the size of the plate, and then n minus 1 stands for the number of plates. If it's 2 plates, it will be 2 minus 1. If it's 4 plates, it will be 4 minus 1 divided by d, which is the distance between the two plates. And then the capacitance is also affected by the material used for the dielectric. That's where the E naught and the ER comes in. E naught is the relative permittivity of free space, which is a constant, 8.85 times 10 to the power minus 12 farads per meter. And then ER, it's relative permittivity of the dielectric, which is material dependent. So it depends on which material you use. So you'll always be given what type of material is used and what is the relative permittivity of that material. Capacitors as resistors can be connected in parallel and also in series, which charge flowing in the capacitive circuit. The charge stored by a capacitor is directly proportional to the charging voltage and the capacitance, giving us the formula Q is equals to CV, where Q is the charge in coulombs with unit C, and then C is the capacitance, and V is the voltage across the capacitance. When a voltage is connected across the two or more parallel identical conducting plates of a capacitor, it stores a charge Q. With opposite parallel polarity plates, between the two plates there will be an electric field lines induced, which starts from positive charge and end at negative charge, as seen in the figures below. The electric field in between the plates where the field lines are parallel is essentially uniform. Later on, we'll also explain how do we calculate the electric field strength of these lines. As explained before, Like resistors, capacitors can be connected in series or also in parallel. So how do you calculate the capacitance of capacitors in series? Capacitors in series, if you have two capacitors C1 and C2, to calculate the total capacitance, we use the formula similar to the one we use for resistors in parallel. So it's the opposite. So the formula will be 1 over Ct equals to 1 over C1 plus 1 over C2, or it can be C1 times C2 divided by C1 plus C2. Then for parallel capacitors, the total will be C1 plus C2. So this is the same as resistors in series. So we use the opposite of resistors. With capacitors, we also have the voltage and current divider. Voltage, as in a resistive circuit, divides when the capacitors are connected in series. So to calculate the total voltage, Vt will be equals to Vc1 plus Vc2, same as we did in resistors. Then to calculate the total charge in series capacitors, they will have the same charge. Qc1 would be equals to Qc2. But the charge in parallel capacitors will divide. Same thing as current in parallel resistors. To calculate the voltage using the voltage divider, it will be for Vc1 it will be C2 over C1 plus C2 times Vt. Why do we have C2 on top but we are calculating for C1? Remember, to calculate the total capacitance in a series, we use the formula like for parallel resistors. We use it for series capacitors. So here it becomes the opposite. C2 would be on top. Then to calculate Vc2, it would be C1 over C1 plus C2 times Vt. Then for parallel capacitors C1 and C2, the total voltage for the parallel capacitors Vt will be equals to Vc1 equals to Vc2. If they are parallel, they have the same voltage. And then the total charge Qt will be equal to Qc1 plus Qc2, same thing as current in parallel resistors. I1 equals to I1 plus I2 equals to IT. Then the current divider, here we have the charge divider. Qc1 will be equal to C1 over C1 plus C2 times Qt. In resistors, we had I1 equals to R2 over R1 plus R2 times IT. So here it's the opposite. So when using the current divider or the voltage divider and the charge divider, remember on capacitors we use the opposite of resistors, but everything else stays the same as resistors. As mentioned before, capacitors are a storage device which they store charge for a short period of time. By connecting a voltmeter to measure the voltage across a capacitor, one can see the increment of a voltage with respect to time, and this is basically the charging of a capacitor. So if you have the circuit below and the switch is on position 1, the capacitor will start charging as shown on the figure, and you can use the formula Vc is equals to Vs open bracket 1 minus e to the power minus t over t close bracket. That will give you the charging voltage at any period of time up until the capacitor is fully charged. Then when you switch this switch to position 2, then the capacitor starts discharging through resistor 2, and you can measure the discharging voltage using the formula Vc is equals to Vs e to the power minus t over t. The t will be the time in seconds, and then the capital letter T, it's the time constant T, which is equals to Rc. The RC circuit is when the resistor is connected in series with the capacitor across a constant voltage supply, DC voltage. The voltage across the capacitor after the switch is connected on terminal 1 which is the charging part, increases exponentially from 0 to Vs. The time constant, capital letter T in seconds, is the time required for the exponential difference across the capacitor to increase from 0 to its final value when it's fully charged, which it takes 5 time constant or 5t. So the T is calculated using the formula T is equals to RC, where T is the time constant, R is the charging resistor, R1, and C is the capacitor. The charging voltage across and the current through the capacitor are respectively expressed as follows in the formulas for VC, and the charging current is IC, and then E is the energy stored in the capacitor. Electric field strength or electric field intensity across and electric field density through the capacitor are respectively expressed as follows. E is equals to V over D, which is the electric strength in volts per meter. It's defined as the force on a unit test charge at a particular location. And then D is equals to Q over A open bracket n minus 1, which is the electric flux density in coulombs per meter squared. It's a measure of the strength of an electric field generated by a free electric charge passing through a given area. The ratio of D over E is called the permittivity of the dielectric. ER times E naught is equals to E, which is equals to D over E. So it's equals to the electric flux density divided by the electric field strength, where E naught times ER is equals to E, and we already explained before that ER is the relative permittivity of the material, and then E naught is the permittivity of free space. The discharging voltage across the capacitor. This is when the switch is connected in terminal 2 and the current through the capacitor are respectively expressed as follows. The discharging voltage, we use the formula Vs equals to E exponent minus small letter t divided by the time constant T capital. Then I will be the total current open bracket 1 minus e to the power minus small letter t over capital letter T. This is the discharging current of the capacitor when there's no power supply. The switch is on terminal 2. Okay, here we have an example where we are given a series parallel circuit and we have to fill in the values for the voltage and the charge. So here we use the same principle as resistors in a series parallel circuit. We've been giving you circuits whereby you have to fill in the values of the voltage and current. So here you fill in voltage and charge. We know that the voltages, if they are parallel, they will have the same voltage. If they are in series, then you add the voltages to get your total. Then the charge in series is the same. In parallel, it divides. So to solve this circuit, look at resistors in Ohm's law. But here, if you have the two resistors in series, the 40 and the 120, you first simplify those two. So 40 times 120 divided by 40 plus 120, or you can use 1 over 40 plus 1 over 120. Then it gives you 30 microfarads. Then this 30 now becomes parallel to the 90. So how do you simplify this? In capacitors, if they're in parallel, you add them. So 90 plus 30 will give us 120 microfarad. Then that leaves you with 120 in series with 30 and also in series with 60 microfarad connected to 225 volt. So now you have 3 capacitors in series. To get the total, CT will be equals to 1 over 30 plus 1 over 60, 1 over 120. This gives us 17.143 microfarad. That's the total. Then to get the total charge, remember in resistors we calculated the total current. So here we calculate the total charge, which is QT equals to CT times VT. So CT is the total capacitance 17.143 times VT, which is the total voltage, This gives us 3.857 millicoulomb. That's the total charge. Then we said charge in series is the same as current in series. So these three, 30, 120 and 60 will have the same charge. Then we can use this charge to calculate the individual voltages. So V30 will be equals to Q divided by C30, which will give us 128.571 volts. V60 will be QT over 60, which gives us 64.286 volts. Then for V120, it will be QT over C120, which gives us 32.143 microfarads. Since the 120 is equivalent to the 90 microfarads parallel to 30 microfarads, therefore the voltage of 120 will be equals to V of 90 and V of 30 microfarads, which is 32.143. And the 30 microfarad is equivalent to 120 microfarads in series with 40 microfarads, meaning that V30 will be equals to V120 microfarad plus V40 microfarads, which is the 32.143 volts. Then the charge for 30 microfarads is equals to C 30 microfarads times V 30 microfarads, which gives us 0.964 millicoulomb. This charge will flow through the 120 and the 40 microfarad capacitors. Therefore, V of 120 microfarads would be equals to 0.964 milli divided by 120, which gives us 8.036 volts. And then V for the 40 microfarad capacitor will be equals to 0.964 milli divided by 40, which gives us 24.107 volts. With all the voltages and some charge acquired, we can easily fill up the table with the values of voltage and charge. We can also use the voltage and current divider rule to calculate all the voltages. Then from there, if you have voltages and capacitance, you can calculate the charge. We can start by simplifying the circuit. We have 40 and 120 in series. Then we simplify that, it gives us 30 microfarads, as you can see in figure 1. Then we'll get 90 and 30 in parallel. To simplify those two capacitors in parallel, it gives us 120. 30 plus 90 gives us 120 microfarads. Then this leaves us with three capacitors in series, 30, 120 and 60. But since we want to use the voltage divider rule, let's further simplify it. Just take the 30 and the 60 series capacitors, make them one capacitor, which will be 20 microfarad. Then it leaves us with 20 microfarad in series with 120. So if you want to apply the voltage divider rule there, Vs2 would be equals to the total voltage 225 divided by 20 plus 120 multiplied by 120. It gives you 192.857. This is the total voltage for 30 and 60. So you can go further, calculate the voltage for 30, which would be your total voltage now is 192.857 divided by 60 plus 30 times 60. It gives you 128.571. Then it means for the 60 it will be the 192.857 minus 128.571. Then if you want to calculate the voltage for the 120 in figure 2, it will be the total voltage 225 divided by 20 plus 120 times 20. It gives you 32.143. Then once we have this total voltage 32.143 for 120, then we can take it to, it will be equal to the voltage of 30, also equals to the voltage of 90 microfarads. Then from there, where did we get this 30? We got it from the 40 and the 120. So it means that your total voltage there, it's there 32.143. Then you apply the voltage divider again to get the voltage of 40 and 120. You can continue from there using this method. Then once you have all your voltages, then you can use the capacitors to calculate the charge in each of the capacitors. Exercise 1. Determine the voltage and charge in respect to all the capacitors in the circuit given in the figure below. Complete the table to reflect your answers. You can do this one on your own, and then we'll share the answers later on. Okay, exercise 2, just read the 3 questions here. We use the formulas that we explained before: time constant, the charging voltage formula, the charging current, discharging current formula, and the discharging voltage formula. And then also the formula to calculate the capacitance of a capacitor. We did explain that as well. Okay, these are the references that we used. Thank you. I will share more examples on our next session.